Well, welcome everybody to our final set of lectures for anatomy and physiology for speech and hearing. So we're on chapter 12, neurophysiology. So I'm so excited. We do get the abbreviated version of neurophysiology just because of the brevity of the course. However, I think you guys are going to be really excited, and this is kind of my own spin a little bit on neurophysiology and what I think is important in terms um, of how cells work in our nervous system. And so I hope you guys enjoy it. I have a lot of links and videos for you guys to watch. So on the next slide, you guys will see that that I have a number of different links for you guys to look at, and they are embedded in the lecture. And this is actually some of these links are updated from the PowerPoint that I posted earlier. So and I did resubmit the PowerPoint, so all these links should correspond with the PowerPoint now listed on Moodle. So here's some more. So you'll see there's quite a few of them. So there'll be a lot of stopping and starting with this lecture in terms of watching those videos. So let's start with just a little bit of review of the basic components of a neuron. To begin, so here's our neuron. Here are our dendrites. Then we have the cell body or the soma. We have the axon, or sorry, the axonal hillock or axon hillock here. Then we have the axon. And around the axon is a myelin sheath. And between the myelin sheath, there are little bare spots where there isn't myelin, and those are called the nodes of Ranvier. And they allow or permit saltatory conduction. And we actually will get to watch a video on that in a little bit and talk more about it. So just be aware. I know we did talk about it a little bit. And then you'll see the terminal end buttons here at the end of the axon. Now, information always travels this way down an axon. All right, so here's our continued review. Neurotransmitters, which are depicted here in blue, are substances or chemicals that are secreted from the terminal end button, which is right here. So that would be right here on a neuron, and now we just have a blown up picture on this side here. Okay, and they communicate with the next neuron. So here's the postsynaptic neuron here. Okay, and it's basically these chemicals work as sort of a lock and key, where they're the key, and then there are different parts of the cell membrane that open in response to the presence of that neurotransmitter. All right, and then we have the synaptic cleft, and that's the space between the presynaptic neuron, which is up here, and the postsynaptic neuron. All right, and now an axon can respond in one of two ways, either through excitation or inhibition. So excitation is increase in the neural tissue activity. So excitation is promoting sending additional axon potentials, whereas inhibition is telling the neuron not to fire. All right, and then we have mitochondria, and you'll remember that those are my favorite organelles, and they use oxygen and glucose to make adenosine triphosphate. And adenosine triphosphate is what we call the cash currency of our cell. So basically, so we have an adenosine, and these are for my chemistry friends out there, and 3 phosphates. And if we cleave one of these bonds, so each one of these bonds, this little dash between the letter, we call those bonds. And if we break one of those bonds, say we break this one here, we release a bunch of energy that looks like that. Okay, tons of energy when we break the phosphate bond specifically, because there's tons of energy stored in the phosphate bond. So here's all this energy being released. Okay, and that energy, these guys here, what I'm calling the energy, is then used to, in this example, used to move those synaptic vesicles down to the synaptic cleft. For a number of things, and to help propagate the action potential or reset the resting cell membrane, cell membrane potential. So, and we'll learn about that in just a little while. All right, so here's some basic physics and chemistry overview. First, we're going to talk about potential and kinetic energy because those principles are super important to understanding how action potentials are sent, and that it's essentially that an action potential being sent is a neuron firing. So understanding potential energy and kinetic energy is really important to understanding how nervous tissue, specifically neurons, send information. So potential energy is energy that's stored in some way. So it has the potential to be used. So the picture here is a ball being lifted up and then held up high, right? And kinetic energy, and we'll come back to that in a minute. Kinetic energy is energy in motion, so the ball moving. Okay. So this is stored energy, whereas this is energy that's being used. So gravity is the stored potential energy. So if you think of a child walking up the stairs of a slide, so that's kinetic energy walking up. Then they have all this stored energy at the top of the slide, and going down the slide, they're turning that potential energy into kinetic energy. So another example would be throwing a ball up, and at the very peak but right before it turns around and comes back down, at that very peak, it has maximum potential energy. It's not moving for a split second, and then drops again. So it goes kinetic, 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 all the way up to the top, stops. That's potential for just a split second or part of a second, and then drops again. That's kinetic energy. All right, so now we get to talk a little bit about ions. So ions are charged particles, and we're going to talk. This is a picture of potassium. Na is potassium. We also talk a lot, or sodium. I'm sorry, this is sodium. We talk a lot about potassium as well, which is K plus. So N plus means that it has an uneven distribution in the number of electrons versus the number of protons. Okay, so if you have more protons than you do electrons, you have a more positive charge. So we denote that by writing Na plus next to the ion. And so if there's equal proportions of electrons and protons, then the particle is not going to have a charge. Okay, so this is an example here. So here's a particle, and so just think of this as the tiniest part of what we understand about the world. It's smaller than a cell. It's a basic element of all things in the world. Okay, so this is just tiny. This is at the chemical level, the tiniest level. Okay, so what we do know is that we have this aggregation of neutrally charged structures called neutrons and positively charged structures called protons. And then swirling around them are these negatively charged structures called electrons. Okay, and if they have an even distribution of electrons or protons, there's no charge. But if we have an uneven distribution of either protons or electrons, we have a difference in charge, and we call those ions. So if we lose a proton, for example, say we got rid of this guy here, we would have 2 electrons here and 1 proton. Okay, and since electrons are negatively charged and a proton is positively charged, we have twice as much negative charge than we do positive charge. So this would be a negatively charged ion. Now, if we lost one of these electrons, say we lost this one, but we had 2 protons, it would be the opposite, right? Then we would have 2 positive, P positive proton, that's how I remember it, P positive, and then N neutral for neutron. If we had 2, okay, we lost the electron, and then we have 2 positive protons, the charge would then be positive, right? Because we have 2 positives versus 1 negative. And that's how sodium is set up. So we have an extra ion, or we have an extra proton, so we have, or 1 less electron. So that's what this is showing here. So here's sodium balanced. Here's sodium losing its electron, its negative charge, therefore making it a positively charged ion, Na+. And that's how we typically find it in the world, and that's how it is and our interstitial fluid, we also call that our intercellular fluid. Okay. All right, so let's talk a little bit about diffusion, and then I want you to watch this video, and it'll make a little bit more sense. So basically, particles are always in motion. Even particles that make up things that are hard, like wood, on tabletops, metal, they all have particles that are moving. They're just compact particles, but they're still bumping into each other at all times. And so that's called Brownian motion. It's particles always moving around randomly. Now we can change how fast those particles move by adjusting the temperature. And we can change how far those particles move by giving them more space. And you want to think of so there's the premise is that these particles are always moving all the time. Okay, and particles, just like, think of people living in a city that want to move out to the suburbs. Particles always want as much space as possible. They want to be farthest away from their buddies as they can. Okay, so they're always going to go to the place where there's the least number of other particles just like them. Okay, so if I'm living in a city and I say, oh my goodness, it is so crowded here, I want to spread out and be as far away from the center of the city as I possibly can. They want lots and lots of elbow room. See? So if you see here, and we call that concentration gradient. So these particles are happiest when they're equally spread out like this. Keep in mind they're still bouncing around, but they have more space to do that. Now, if we have a high concentration gradient, being that there's more particles in this one area of the fluid, for example, and very few, or to none, particles over here, those particles are going to, because of this random motion, are eventually going to diffuse or spread out into this fluid in sort of this equal distribution like this. And that's what they always want to do. So let's talk about this from a potential and kinetic energy perspective. So these particles being all aggregated together, closely packed together, that's potential energy. Okay? Now the minute that they're allowed to move away from each other, that's kinetic energy. Okay? So that kinetic energy then allows these particles to spread out as far as they want. Okay, so that's important later when we start to talk about concentration gradients of sodium and potassium ions inside and outside of the neural cell membrane. So go ahead and pause this video, and then go ahead and click on this link, and it'll give you a better overview and picture of how diffusion works. All right, okay, so now we're going to talk a little bit about electrochemical gradients and what an electrochemical gradient is and how that is set up. Like, how is it even possible that we have this electrochemical gradient? Okay, so we talked about ions. Ions are charged particles, right? So we have a positively charged sodium ion here, positively charged potassium ion, negatively charged chloride ion, and then we also have proteins. Proteins are kind of the building blocks of all the structures in our body, and we're familiar with it in terms from a nutritional perspective, right? Where we need to eat protein so that we can rebuild tissue. Well, protein also live within cells, and these cells within the neuron these proteins within a neuron are negatively charged, so they have a charge as well. Okay. So this picture here is showing the outside of a cell and the inside of a cell. So let me draw a picture really quick. Okay. So here are my dendrites. As you can see, you do not have to be an artist to learn anatomy. Here's my axon out to the terminal end button. So I just want you guys to get a better understanding of what I'm talking about. So when you look at this picture here, this is inside the cell, this is outside the cell, okay? So if you look here, this is inside the cell. Okay, so here's our negatively charged proteins. I'm just going to put a negative there. Negative, negative. And then we also have our potassium in here. So I'm just going to put K plus. Lots of K pluses inside of our cell. So that's potassium, okay? And then on the outside of our cell, we're going to have lots of sodium. Just like that. Okay, and we're not going to talk a lot about chloride. Okay, it does help balance the charges in the outside of the cell membrane. However, the big players are the sodium-potassium relationship. So do know that we do have chloride on the outside of the cell, quite a bit of it, but it's more important for us in terms of understanding propagations of action potentials when we talk about sodium and potassium. Now, in general, the inside of the cell is more negative. So I'm just going to write that really quick. Cell, Shanna, negative. Okay? So it's more negative on the inside. And since there's this gradient, it's going to be more positive on the outside. Okay? This is all at resting membrane potential. This is when the action potential is waiting for, here, we'll just go. So this is at resting membrane potential. Which is actually negative 70 millivolts. Okay, so that means that, so resting membrane potential is when the cell is prepared to be able to send an action potential, okay? So it's prepared to be able to, oh, wrong guy. I'm going to get rid of this. Well, try not to pay attention to that arrow. But it's preparing to be able to send information this way, okay? And it's got to cross that axon hillock, right? Which is right here. Okay, so this is our soldier ready and waiting, prepared, done all the training, got it, has everything set up, ready to send that information. Okay, so this is at resting membrane potential, meaning that it's negative 70 millivolts. So it's negative 70 millivolts compared to the outside here. Okay, so this relationship is negative 70 millivolts lower than on the outside of the cell. And now the one question I had, which is a great question, is why does sodium, if sodium is positively charged and so is potassium, why is it more positive on the outside of the cell? Because both of them have positive charges. And one of the main answers is that sodium is more positive than potassium. So if you look on this picture here, you'll see that the sodium, they're bigger particles and they have a more positive charge. So they play a bigger role. And you'll see the Na2 plus versus the K plus. Okay? So that's the main reason. Okay, so I really, and calcium plays a role too, but we're not going to talk a lot about that. Okay? That is more important when we get to muscle contraction. So what I would encourage you guys to do is to draw a picture like this to remind yourself of what resting membrane potential looks like. So this is baseline here. And then you'll remember, is sodium on the inside or outside? Is potassium on the inside or outside? What's more positive? What's more negative? Okay, so do be able to draw that picture, and it'll help kind of get things going. So here's another picture, just like the one I drew, but this is just consider this part of the axon. So that would be from, this just, let's see, if I took a part of the axon like here to here and blew it up, that's what this next page looks like. Okay, so that's this guy here. All right, so this is exactly the picture that I just drew you guys. So we have the sodium and then potassium, sodium on the outside. It's more positive, so that's the red here, more negative on the inside. All right, so the next thing that we get a visit about is passive and active transport. So if you think back to learning about potential energy, kinetic energy, and diffusion, passive transport will make sense. So so after the cell's been depolarized, we have an imbalance. So basically, okay, say the action, we want propagation of the action potential. Okay, so here's our picture again. When that happens, sodium is going to go into the cell. Just like that. It's going to travel in, okay? And potassium, a little bit after, is going to rush out. And there's no ATP that's needed. So we don't have to use any energy to do that. It just happens because of this passive transport. And this passive transport occurs because of that, remember that principle of diffusion where particles are always moving around and they want to go to the area of least resistance. So if I have, so here's my cell membrane. If I have more sodium on the outside and no sodium on the inside of the cell, they're like, the sodium's basically saying, oh my gosh, there's all this free real estate inside of the cell. I'm going to rush down it just like a child going down a slide. I'm going to rush into the cell because I want to be farthest away from my buddy sodium. I'm going to go inside the cell. Okay? Now he has all the elbow room that he wants. Okay? The same thing happens when we're talking about potassium. Because there's more potassium on the inside of the cell and less on the outside, it's going to want to do the same thing. So here we are. Action potential is being propagated. We have sodium on the inside, or potassium, sorry, and potassium says, I really, really, really need to get out of here. So he actually goes this way and leaves and heads out of the cell. Okay, that happens via this process of passive transport. Okay, it uses the concentration gradient that we just talked about to cross this plasma membrane, which is right here. Okay, no energy is needed. Whereas active transport uses that adenosine triphosphate, okay, to basically reset that electrochemical gradient, which is this. And I actually think I skipped over what that electrochemical gradient is, that unequal distribution of charged particles on each side of the membrane, whether it be inside or outside. So since we have more potassium on the inside versus the outside, there's a gradient, right? Where we have a higher concentration gradient of the potassium on the inside of the cell versus the outside of the cell. So those potassium ions naturally want to go to where there's more free real estate, which is on the outside of the cell. Okay? So, and it takes energy to create that electrochemical gradient. We have to push those potassium ions back into the cell, back into the inside of the cell. And that takes energy because we're moving up the concentration gradient. We're taking all of those those potassium ions from the suburbs and pushing them back into the city. It's like rolling a ball up a hill. It takes energy. And then letting the ball roll back down the hill, that's the potential energy then being used and put into kinetic energy. So, and that's that passive transport. But the active transport occurs when we've got to push the potassium ions back up against the concentration gradient to set up this resting membrane potential. Okay, and we call it the electrochemical gradient because we use electrically charged chemicals, which are sodium. So sodium's the chemical, and then we take away one of its electrons, making a positively charged chemical, which gives it sort of the electrical property. Okay. So I hope this is making sense. I really enjoy this topic. So and I'm excited to meet with you guys too, so we can even talk about it more if you want. Uh, so um, so in order to create that electrochemical gradient at resting membrane potential at negative 70 millivolts, which means that it's more negative on the inside of the cell versus the outside of the cell, we need to use adenosine triphosphate. Okay, and that happens here, and using this protein channel. Okay, and it's called the sodium potassium pump. It's on the next slide. And let's actually move to that. Let's move to the sodium potassium pump. So this is a picture of it. And actually, I encourage you to watch this video, and then you can stop and listen to me some more if you'd like. Either way, but do watch this one, and do watch the voltage gated potassium channel. That's going to help you put together the whole propagation, like how we open up the sodium potassium channels and let them rush down the concentration gradient. And there's also a couple videos too, and I'll draw one more picture talking about the whole propagation. But first, I just kind of want to give you the background of it. So here's our sodium potassium pump. So, and it's doing all the hard work. So think it's cleaning up the mess after we've opened up those voltage gated potassium channels, and where we let the potassium run out of the cell and let sodium run into it. It's got to clean up the mess. It's got to reestablish that resting membrane potential. It's got to reestablish that concentration gradient. So it's got to do that by pumping sodium out of the cell and pumping potassium back into it. Okay? And so for every 3 sodium, it pumps 2 potassium back in. And it uses this adenosine triphosphate to do that. And this is all part of this active transport. So go ahead and watch that. All right, so here's my, this is my picture of a sodium potassium pump. All right, so this is after we've opened up those voltage gated channels and let sodium into the cell and potassium out of the cell. Okay, now we need to clean up the mess. So we're going to do that by using adenosine triphosphate, which is right here, and collecting 3 sodium ions. So we're gonna kick them out, and then we're gonna grab 2 potassium and push them back in. Okay. So go ahead and try to draw this picture as well. This is an important one in terms of understanding the sodium potassium pump. And if you're feeling overwhelmed about the whole process in general, that's not uncommon. There's a lot of things going on. Just stick with me. Just stick with me. I promise you it's going to come together in just a little bit. And actually this is a great segue into action potential propagation. So let's see. So I think I talked about substitutory. Okay, good. Okay. So action potential propagation occurs when we've had enough information coming in from the dendrites in the cell body, from other neurons telling this cell, you need to fire. Okay? So enough information occurs here, and actually it looks like, let me get a new picture for you. All right, so let me draw you guys a neuron again. So, so action potentials, like I said, are all or nothing. However, we have these graded potentials at the level of the cell body. So I might have another axon that that is terminating at this dendrite, okay? And it's saying, I want you to send this information that I have. So I'm going to give you this excitatory postsynaptic potential. I'm going to say, I want you to fire. Now here's another one. Here's another neuron that's saying, I have similar information. It's really important that you send it. So I also am going to vote to send that action potential. I'm going to give you a positive excitatory postsynaptic potential. Okay? And here's another one. And this one's saying, yep, I totally agree. I too am a neuron with the same kind of information, and I want you to send it. So I'm going to add to that decision. So this is democracy at the level of the neuron. All right, now I have another neuron that says, hold on, team. I actually don't think that we should be sending this information. I'm going to vote no. Okay? And then I have another neuron that says, I agree. I'm going to vote no too. We do not need to send this information. Okay? So at this point, we have 3 yeses and 2 nos. So in general, if we subtracted 3 from 2, we would have 1 difference, right? Which is the positive, saying yes, we need to send that information. Okay? And if that vote is strong enough, say it's not, say one difference in vote is not enough to send that potential, which is this graded potential. So we have action potentials and graded potentials. Graded potentials occur here at the level of the dendrites and cell body. Action potentials occur at the level of the axon. So at this point, even though we're getting all of this information sent via action potentials, it needs to be integrated here. So remember me talking about the gray matter where all the thought occurs and the integration of information. That's happening here at the level of this graded potential. Graded meaning that we're going to add all of these excitatory postsynaptic potentials and all these inhibitory postsynaptic potentials to make a decision about whether or not we're going to send that information. Okay? And at this point, let's say that one positive is just not enough. But then we have one more neuron that says, yes, I really do need you and want you to send that information. You have to. You have to send it, okay? So then we get one more positive. Okay? So that's one way to get the information, to get enough positive votes to send the action potential via this graded potential. Another way is to have one axon fire a number of times. They say yes, 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 we do need to send it, giving us more positives, okay? So say now that 4 is enough to get that information far enough through the cell body to hit the axon hillock. So we're going to send these over here, then we're going to trigger the gatekeeper, which is our axon hillock, to send that action potential. Okay? And so action potentials are all or nothing. Just like sending an email, once you push send, it's gone. Okay? All of the thought integration has occurred. We've made the decision, so here we're writing the email. Here we're sending the email at the level of the axon hillock. Okay? So this is graded potential. This is action potential. Now let's talk about action potentials. So we do know now, after talking about it a little bit, that we have potassium on the inside of the cell, more potassium on the inside, okay, and it is more negative on the inside. And we now know that we have more sodium, and it's a bigger molecule on the outside of the cell, and it is more positive at resting membrane potential. Okay, so say we have not triggered this action potential yet. Okay, we're just getting ready to. And then along that cell membrane, we have these guys called voltage gated ion channels. So there's one, There's one. Here's another one. Okay. And then in between them, we have sodium potassium pumps. The janitors of our cell. The hard workers, the ones who use all the energy. Okay? So say we vote yes, and we get a positive here that says send that action potential, you need to go. Okay? When that happens, this electricity from deciding to send the action potential opens up this voltage gated channel, this first guy right here. So this guy opens it up and says, you know what? I want you to let potassium out. So let's put in a couple more potassiums in here. Okay. Go ahead and let potassium out because he wants out, he's got too many buddies inside. Okay. And so potassium rushes out of these voltage gated channels. Okay. All right. In addition to that, we also have, and actually this happens first, potassium or sodium gets to rush in because it too doesn't want to be out in the city, right? And there's lots of potassium on the outside. So it rushes in via these voltage gated channels. Okay. As the action potential propagates, it opens more and more of these voltage gated channels along the way. Opens another one here, opens another one here, all the way down the axon. Okay? And once those voltage gated channels are open, they close almost immediately. So action potentials can only be sent one way, this way. They cannot be sent backwards towards the cell body. They only move away from the cell body. Okay? And then we have the sodium potassium pumps reestablishing that resting membrane potential. Okay, so I hope that helps clear things up a little. I want to save it. All right, so go ahead and watch this video, and it should make sense for you guys a little bit more. All right, the next thing that we wanted to talk about was saltatory conduction. So here's our myelin sheath and then our nodes of Ranvier. And so we have our action potential, the electrochemical gradient, the electricity basically caused by the action potential is able to kind of hopscotch over this myelin sheath to each node of Ranvier. And that allows us to send the information much quicker. We also do have some of part of that electrochemical gradient, or the shift of actually sodium being pushed this way that occurs, which helps send the information down the axon. But this kind of dissipates. So really this is the primary driver in terms of sending that action potential quickly. So go ahead and watch this video, and it'll help put saltatory conduction a little together for you guys a little bit more. All right, now we get to talk about, well, I already did kind of foreshadow generator and action potentials. I also call them graded potentials. That's the same thing as a generator potential. And then action potentials are that all or nothing. So, so this is resting membrane potential, that negative 70 millivolts, okay? That's where we have sodium on the outside, potassium on the inside of the cell. Okay, nothing's happening. We're a cell that is ready to fire. Okay, then we get enough information at the level of the cell body, meaning that enough dendrites have picked up enough excitatory postsynaptic potentials to agree that we need to send the information. So there's a triggering at the axon hillock, right? It's saying that we need to propagate that action potential. We need to send that information. So the first thing that happens is the sodium voltage gated channels open, allowing sodium to enter the cell membrane. Then the potassium channels open just a little bit after. And you'll see on this graph that we're getting more and more positive on the inside of the cell. So this is measuring the inside of the cell, okay, that membrane potential. We're becoming more and more positive on the inside of the cell, okay, and the potassium channels open. Then at the very peak, at the most positive, whereas it's actually more positive on the inside of the cell than the outside of the cell, although that's not typical, right, at resting membrane potential, the sodium channels close. So remember, sodium channels open and close first. Then later, the potassium channels start to close. Okay, but there's this time where it's called the relative refractory period or hyperpolarization, where you're not going to be able to fire another action potential. You actually get more kind of over. You become too negative inside of the cell. Okay. So here we're starting this repolarization phase, whereas the sodium potassium channels are reestablishing resting membrane potential, but they actually become a little bit um, too too good at their job, and they actually just like they kind of overshoot the target, just like you would if you were in a swerve to miss a deer and you overshoot. So the same thing happens with the sodium potassium pump, and we become more negative than 70 millivolts, which is this resting membrane potential where the action potential can be sent. So then we have these leaky potassium channels that allow the potassium, some of it, to leave the cell, making it just enough positive, enough more positive to equal that negative 70 millivolts, which is that resting membrane potential. So here's a picture, and I encourage you to draw this picture out, or even just print this slide out and go through the exchange of events that I just talked about. And here's another example of that. So here's resting membrane potential at negative 70 millivolts. Then we have depolarization. So resting membrane potential means that the cell membrane is polarized, just like you have poles on a magnet, where you have one pole that's more positive and one pole that's more negative. The same thing happens at the level of the cell. So it's the negative part is inside the cell and the positive part is outside of the cell. So it's polarized. Okay, just like a north and south pole is polarized. So we want to when we're depolarizing it, we're allowing this membrane potential to go closer to zero. And actually, I want to go back up here for just a second. You'll see that even though zero would be optimal, right? That'd be equal. We overshoot zero too and become too positive, just like we overshoot our negative 70 millivolts here. So there's a lot of overshooting. Okay. So there's resting membrane potential. Then we open the sodium channels, which allows depolarization to begin. And then we have our sodium channels close. Potassium channels start to close. Oh, I should have had potassium channels right here. So potassium channels open right here, and they start to close. Okay, and then we have this hyperpolarization. So during this repolarization phase, that's when the sodium potassium channels are working. Then we have this hyperpolarization, which is about 0.5 milliseconds, where the sodium potassium pump is kind of overdone its job, and we're below that negative 70 millivolts, which is resting membrane potential. So these handwritten tutorials, I just found these, and I think they're wonderful. So go ahead and actually walks through 3 different phases of action potential propagation. So watch each one of them. They're really nice. I think they're really wonderful, actually. All right. So there are a number of different neurotransmitters, and this class is just too full, and you have a whole class on neuro. So I'm only going to teach you 2. One that's a big part of the peripheral nervous system, and one that's a big part of the central nervous system, just to start being familiar with neurotransmitters and that they have names and so forth. So acetylcholine is a big neurotransmitter in the peripheral nervous system, and it's responsible for telling muscles to fire. So they're located at the juncture between a neuron and a muscle. So that's the neuromuscular junction. And they're excitatory neurotransmitters. Now there are inhibitory neurotransmitters as well, but this one is excitatory. Then we have endorphins in the central nervous system, and you guys might be familiar with these. You know, if somebody's telling you to exercise so you can have your endorphins released, it's a pain regulator in the central nervous system. So cool. I just hope, kind of, I guess, tickle your imagination in terms of learning about neurotransmitters and the different types. I just think neuro is fascinating, which is probably why I spend so much time on it in this class, or expect you guys to learn so much. But it's a big part of our field too, and it'll really prepare you for your class coming up here in neuro. So I hope you guys like neuro, and that I've been able to kind of impart some enthusiasm for it. So here is a video about neurotransmitter release. I'm a very visual person and I like videos, so that's why I give you guys lots of them. So go ahead and watch this guy. All right, so we're going to talk a little bit about muscle contraction. So here is a picture of a muscle blown up. So we start here at A. So here's a picture of your deltoid. Then we're going to look at the muscle fasciculus, which is just an aggregation or a grouping of muscle cell fibers. And then we break that down to see just here's the muscle fiber broken down even farther. And then we look at this structure called the myofibril, which is just a smaller section of the muscle fiber. And you'll see that we have these different bands or zones. So we have a Z, an H zone, a Z line, an A band, and an I band. So if you look here, if we break it down even farther, and you look at the H zone, okay, and the F zone, you'll see that between the H and the E, you'll have this myosin filament, okay? And on the next picture, you guys will see it. But actin and myosin, and here's actin here. Actin and myosin work together in sort of this cross-linked fashion. Think of like, what's a good example? So think of an ice climber climbing up ice with those with the, gosh, what are those called? Ice cleavers. That's not the right word. But they kind of, they link into the ice one step at a time, okay? They click in, then they release, click in and they release, click in and they release. That's how this process of muscle contractions work between actin and myosin, which are the main players. Okay. So here is a video, and actually, I kind of have a story about how this actin and myosin work together, and it's a story that was told to me to help me understand the process of muscle contraction. So this is at the very molecular level of muscle contraction. So go ahead and watch the video. It just is showing this picture animated. So here's myosin. I'm going to introduce you so that I'll kind of talk to you about this from a soap opera perspective. Okay, so here's myosin, and myosin is the handsome gentleman, or so-called gentleman, that would like to take actin out to the movies. Okay, so here's myosin trying to date actin, which is this really beautiful girl. Okay, lovely, lovely girl. Okay. However, actin has some very suspicious and protective parents called the troponin complex, which is right here. Okay? So here's the troponin complex. And the troponin complex actually covers the binding site of actin, okay, which doesn't allow myosin to make contact with actin. Okay? However, if we have the adenosine triphosphate come in, or calcium comes in and allows this troponin complex to open. Okay, and myosin could then hook onto actin's binding site. Okay, and the only way to unhitch myosin from actin is by firing this adenosine triphosphate. Okay. So you have to cleave adenosine triphosphate. So go ahead and watch that video, and I think it'll make sense a little bit more. So remember, troponin covers up the binding site. Myosin is actually, and then really what myosin wants to do is bind to one actin binding site, let go, and then bind to the next one, and the next one, and the next one. Okay, so he's kind of a dirty rascal, like this. Okay, and that allows that muscle to shorten. So if we look back here, basically, when the muscle contracts, actin is going to be pulled in towards myosin this way. Okay. All right, and so there are a number of there are two different main muscle fibers, and there's intermediate as well. But we have slow twitch and fast twitch muscle fibers. Slow twitch are responsible for posture, whereas fast twitch are responsible for fine and rapid motor function. So here's a fast twitcher, and here's a slow twitch athlete. So think endurance and think sprinter. And these guys easily fatigue. They actually use creatine phosphate instead of which you don't need oxygen to produce. So, but it's easily exhaustible. So anyway, these you can only contract your sprinting muscles for so long, where these endurance muscles can be used for a very long period of time, which is why endurance muscles can run for so long. And they also have a different morphology or shape. So the fast twitch are thicker muscles. Actually, the fiber is much thicker than these endurance muscles. So that explains some of the physical differences in the athlete. All right, so here we are. These pyramidal and extrapyramidal tracts are on your guys' terms to know. So I do want to go over them for you, and you will get more neuro. So this is just a nice overview. So your pyramidal tracts are these tracts of neurons that start at the motor cortex, which is up here in the frontal lobe, and specifically most of them are at the primary motor strip, which is right here. So this is the brain. This is the brain stem, and then here's the spinal cord down here. Okay. And so it's basically this pathway of neurons that travel either down the spinal cord or into the brainstem and then out to control muscles of the face. And then the ones that go down the spinal cord control muscles of the body. And all of this is, think of this as the as voluntary motor control. These are you're making decisions about how to move the muscles in your face or in your body. Okay, so that's the pyramidal tract. So it's direct conscious control. Okay, this is the tract that allows that to happen. And we call it the pyramidal tract. There's these structures called medullary pyramids in the medulla, and I think I talked about them in the neuroanatomy dissection video. But it's a primary place for decussation. So here's decussation of the pyramid, and then here's where the motor neurons travel down. So it's just a bulge in the brainstem where you can see where those tracks travel down through the brainstem to the spinal cord. And so we call them pyramids. And so that's the pyramidal tract because those neurons actually travel through that pyramidal tract. And there's actually two pathways, the corticospinal and the cortical bulbar. So the cortico, so this is the cortex, and the root for that is cortico. So it travels from the cortex down to the spinal cord. So that's the corticospinal tract. And then we have the corticobulbar. So the bulbar is another word for brainstem. So it travels from the cortex, right here, tells you, to the bulbar region of the brainstem, which is right here. So, and this is actually a nuclei of one of the cranial nerves. Okay, and we call those these are lower motor neurons, and these are upper motor neurons. And the only difference is that these guys leave the central nervous system. So these are nerves, whereas these are tracts, right? So that's the only difference. All right, so then let's talk about, so the extrapyramidal are kind of the opposite in terms of motor control. So the pyramidal are responsible for voluntary control. Extrapyramidal are responsible for that involuntary control. So they're in charge of reflexes, locomotion, postural control, and they really involve structures in the central nervous system, such as the medulla, and the pons, so medulla, pons, cerebellum, and basal ganglia. So here, you don't need to know the tract specifically, just know its general function. Okay, it's the involuntary control, reflexes, locomotion, postural control, and uses all these structures to do that, all this background motion. Okay. Well, congratulations, you guys. We are now formally done with your guys' lectures for anatomy and physiology for speech and hearing. So I really hope you guys enjoyed it. I know it was a lot of hard work, a ton of hard work, and a lot of time. But I've been really blessed and thankful to have you guys as a class, and to be able to talk to you guys about some of the things that are really interesting to me. So well, good luck on your guys' final, and I look forward to talking to those of you who are going to join us on Saturday for a little question and answer session. All right. Farewell, guys.